Thanks a lot to the organizers for inviting me to give this talk. For me, having spent part of my PhD during a pandemic, it's a lot of fun to get to travel to places and actually talk to people. So today I want to tell you about a recent work called Classical Verification of Quantum Learning, and I'll also mention some ongoing work that we're currently doing along these lines. Before I say anything about the content, I should say that this is, of course, not my own work, but it's work that I did with a great team. So here are Marcel, Marius, Alex, and Ryan, who are on the paper that's already on the archive. And now for the ongoing work, we've also joined forces with Jens. Okay, I'm not quite sure why it's not moving anymore. Now it's moving. So all of these people are very heavily involved in what I'll be talking about. So what is it actually that I want to tell you about? The motivation is very simple, and it actually comes from a classical machine learning paper by Shafi Goldwasser's group from UC Berkeley. And so this is me. I'm very classical. I have some, let's say, shitty data, and I'm not very good at computing. Still, I'd like to solve some kind of machine learning problems. Now, given that I don't have good data and can't compute, somebody else has to do it for me. So what I would like to do is, say, talk to, I don't know, Google, IBM, OpenAI, who are still classical, but pretty good at computing, and they have high-quality data. And now the idea is that I want to interact with them such that, in the end, what I produce is a good hypothesis, so a good mapping from inputs to labels. Now, this is easy if I trust them. If I trust them, I just tell them, please solve that machine learning problem for me. They send me the solution, I'm happy. What do I do if I don't trust them? And this is the insight of this paper, who developed the framework for interactively verifying the interaction between a weak learner and a strong learner, even if the weak learner cannot trust the strong learner. So this is the classical perspective. Now, if you know me, of course, I'll put quantum on this. And the way we did it is to say, OK, this is still me. I'm still very classical. But maybe somebody else is quantum and can solve quantum machine learning problems. Now, I should say that this presupposes a lot, right? This presupposes somebody can solve a quantum machine learning problem for me. I'll show you on a theoretical side. I'll show you an example of such a problem, and I'll show you how we can actually verify it. But this presupposes a lot. The task remains the same. So I, as a classical weak learner, I'll call this verifier in the computer science language. I want to make use of the power of a strong quantum learner, which I'll call prover, to solve a learning problem, even if I do not trust the prover.
Mm-hmm. So use it means to replace your answers by this, or interact in any way? Or?
Yeah, so use it means something like I pay for a subscription service, which allows me to send requests or queries to I don't know, Google Quantum, IBM, Xanadu. And they then send me back answers to my requests. And then I process these answers in a way that lets me decide whether they're actually giving me truthful answers. And if they were truthful, in the end, I will have solved the problem.
So your learning is there to decide whether or not to accept their learned answer, basically.
To some degree,
learn a bit, right?
Yeah, to some degree. Yeah.
Can I ask, what in your framework prohibits the use of quantum fully homomorphic encryption and just encrypt the data and bring it back?
Yeah, so you can try something like homomorphic encryption, but one thing I want to emphasize is that you cannot solve this problem by just verifying quantum computation, because what you could verify would be that the quantum prover is doing what they're supposed to do. What you cannot verify this way is that they're doing it on high-quality quantum data. Because you're just verifying their computation, you're not verifying their resource that way. So this is the additional ingredient here, that you're not only verifying a computation, you're also verifying the quality of the resource, in a sense. And yeah, this is why homomorphic encryption is not alone enough, at least to the best of my knowledge. Yeah?
So are you making any assumptions about the untrusted party? Or are you completely untrusted, or are you assuming that they have some data or they have a quantum computer?
Mm-hmm. For what I'll be talking about today, I don't make any assumptions. They're untrusted. But what you'll see in the result I prove is kind of, if they do wrong things, then I, as the classical verifier, might just not succeed. So that's the price you pay for not making any assumptions about the quantum proof. So this is the motivation of the talk. It will actually be some time until I give you the formal definition of what I mean by this verification. In fact, I will only give it to you when showing you the result, because it's easiest to present it that way. But for the way, I want you to keep in mind this guiding question. So what we're looking for is a learning problem with two features. The first feature is it should be intractable for classical learners, but feasible for quantum learners. And the second feature that we want is that a classical verifier can efficiently, verifiably delegate this problem to a quantum prover. So the first point tells me if the verifier were just on their own, they wouldn't be able to solve the problem. Now, they know that the prover on their own would be able to solve the problem. And the second point now tells us that we want the verifier to be able to outsource the work to the prover, so that even if they do not trust the prover, in the end, they will have a solution of the problem. Robin.
Where's this quantum data coming from? Like it's coming from outside, or is the quantum learner creating it themselves?
I'll get to that point. It's coming from, I mean, in principle, I'm not making assumptions about this. I'm imagining it's coming from the outside. I'll be working with a quantum data oracle that admittedly is not practical, but it's a proof of principle result.
But if it's coming from our side, what does it mean for a classical learner to be able to solve the problem? Like the classical learner cannot handle quantum information. Right? So like it's just
the classical learner doesn't at any point do anything in quantum. So the classical learner has classical data, this communication is classical, and this thing is also classical.
But I mean, like your first requirement says that it should be an intractable learning problem for a classical verifier, but the classical verifier just vacuously cannot learn anything about quantum states.
So that's a very good point. So what I want is that for the classical verifier with the classical data, it's intractable. For the quantum prover with the quantum data, it's tractable. So I'm making the quantum side stronger in two ways. I give them quantum computing power and I give them quantum data access.
Would you give the classical verifier some analogous classical data that's similar to the quantum data that quantum person would have received?
Yes.
Sorry, but in your second slide, the next slide, you're looking for a learning problem that has these properties, right?
Yeah.
So it means you can set what the quantum states are part of the learning problem. You can demand them to be of a certain shape, right?
I'm going to look at a specific kind of oracle.
In which case they can be the quantum encodings of data for blind quantum computing, which has verifiability over quantum data as well, right? Because there are verification protocols where the user would encrypt the data in a particular way, and you just demand those to be the part of the input.
But then you would have to force the prover to work with those states. Can you do that?
No, if they throw it away, it's going to fail the verification procedure.
Okay, yeah. Then that might actually also work. Yeah.
So, and are you allowing communication going both ways?
Yes, I'm allowing multi-round communication going both ways. Maybe I should have drawn multiple arrows here. All right. Cool. So this is my plan. Given the amount of questions, it's probably ambitious. I'll first try to give you a bit of an intro to computational learning theory. So this will be like hardcore CS, but I'll try to make it interesting. And then I'll take a little bit of a detour, because actually to get to the goal that we want to get to, we have to do something intermediate, a problem called agnostic quantum learning, where not so much was known, and we propose a new oracle with which you can solve it. Then we actually do the verification, and if I magically have time, I'll tell you a little bit more about the limitations of our new quantum data. So first of all, classical computational learning theory and the step to make it quantum. So here's a crash course. The crash course is about alpha-agnostic learning. So what's this about? You have a learning problem with a benchmark class. This is the class that you want to be at least as good as. What you're using for it is a model class. So this is the class of models your learning model can output. That would be maybe a certain class of neural networks, certain class of quantum circuits, certain class of support vector machines. The next thing you have is a distribution class over inputs and outputs. This describes the possible data that you could be facing. So you should think of the n-bit strings as inputs and this single bit as output. So this is a simplification I'm making. Of course, you could be interested in other spaces, but for computational learning theory, let's stick to this bit setting. And then you have an oracle, which is how you get access to your data. So this oracle might give you random examples, or you might be able to actively query it, or you might be able to statistically query it, or it might be a quantum oracle. And now I can formulate my definition. It's a bit of a block of text, but I hope I can make it understandable. So what do I mean by alpha-agnostic learning? And let me be very precise. I want to study alpha-agnostic learning for the benchmark class via the model class with respect to the distribution class from the oracle. This is important. So all of these classes quantifiers here are important. And the requirement is that no matter what your data generating distribution is in that class, if you're given access to the oracle for that distribution and some confidence and accuracy parameters, then with a high enough probability, you'll output a model from your model class such that the following is true. The probability that the model that you output misclassifies a freshly drawn sample. So you draw a fresh sample, and you look at the probability that the bit string your model outputs is different from the bit that you got in the sample. You want this error probability to be at most alpha times the best error probability you could have achieved in the benchmark class, plus some small error epsilon. Okay? So this is alpha-agnostic learning. Alpha is this prefactor here. Ideally, you want alpha to be 1. I have to introduce it here because we can't always achieve that. What you might be used to is a scenario where this minimum is actually 0. So if your benchmark class can perfectly describe the data, this minimum will be 0, and then you're just trying to achieve performance at most epsilon. For our purposes, it's actually important that this term is in general non-zero. I won't show you the details for that, I just want to mention it. Yeah, Ivan.
Can we set b equals m?
Yes, we can set b equals m. That happens often. Again, this is one thing that I have to do for technical reasons, because not in all our results is it the case. But yeah, we can set those to equal. Sean.
So now that everything is on the screen, can you just explain again what the qualitative role of the benchmark class is?
Yeah, so the benchmark class is how good do you want to be? So how good does your performance have to be? This is what you're comparing to in the sense that you're looking at the optimal performance over the benchmark class. So for example, say you look at neural networks of a certain depth, then you want to do as well as the best neural network, but maybe you're using a different kind of model class. Okay, so this is the mathematical definition here. Now, we don't want this just in any way, we want it to be somewhat efficient. And in this talk, we'll care about both sample and computational efficiency. I'm a bit imprecise here. I call this sample even though the oracle might be something else. But think about an efficient number of oracle calls and an efficient computation. And then for this talk, I'll make some simplifications, because otherwise it gets a bit lengthy. I'll only talk about classical and quantum example oracles, so where you sample from the distribution or you get quantum examples. I'll also always assume that these n-bit inputs are uniformly random. We can go beyond this a little bit, but for simplification, let's do this. And you'll hear me speaking about two cases that I distinguish. The first is the functional case, the second is the distributional case. By functional, I mean that every distribution in your distribution class is actually a distribution over inputs, in our case, a uniform distribution, and then a deterministic function that maps the input to the output. So that means all of the randomness in your distribution is just in the random choice of the input, and then there's a deterministic mapping. And for those of you who know this nomenclature, you would call this realizable if the function is always in the benchmark class, but that doesn't have to be the case. So I call this functional because there is a function.
Should that be log 1 over delta at the top?
That depends. Usually it is log 1 over delta, but the definition is usually given just in terms of 1 over delta. But you're right, all the guarantees we have are log 1 over delta. Yeah?
So, with the previous agnostic learning, shouldn't this really be called like comparative agnostic learning because you have a separate benchmark?
Yeah, that's a very good point. So there was a super cool paper in ITCS last year, I think, about comparative learning that talks more about this model and benchmarking class. Yeah, you could call it that. Okay, so this is the functional case. So what's the distributional case? The distributional case is where you don't have that. So no extra assumptions. There are general distributions about inputs and outputs. Robin, you have a question.
Your classes B and M are also function classes.
They are function classes. For one of our results, they can be randomized functions, but they are, think of them as function classes, yes. Okay. So I need another very short crash course about how you learn using what's called Boolean Fourier analysis. I'll be super vague here. So you know Fourier analysis in terms of sines and cosines. That's the right thing to do if you look at functions over the real numbers. If you look at functions over n-bit strings, which I'll just write as xn, you need to choose a different orthonormal basis. For completeness, this is the orthonormal basis. They're called parity functions. And then these are your Fourier coefficients. So think about this really, it's the same as Fourier analysis over the real line. You pick an orthonormal basis, you expand in that orthonormal basis. And the cool thing is that Fourier analysis and learning are tightly connected. So for example, if we have a distribution with uniformly random inputs, and then the labels are random, and we know their conditional expectation. So this phi is just the expectation of the label given the input, or in other words, it's the probability of the label being 1. Note that this might be between 0 and 1. Only it's equal 0 or 1 in the deterministic case. And now if you try to match that distribution with a deterministic function, and okay, we relabel from 0, 1 to -1, 1, because that's convenient, and we do the same relabeling for the conditional expectation, you can write this error probability that we cared about before in terms of the Fourier coefficients. So the error probability is 1 minus essentially the inner product of the vectors of Fourier coefficients divided by 2. This is I don't know, half a page computation. If you're slow like me, then it's half a page. But this shows you that if you're able to find a function f, or g in the -1, 1 version, whose Fourier spectrum matches the Fourier spectrum of the conditional expectation well, then you've won. Then you achieve a small error probability. So this is on a high level why Fourier analysis is good for learning. There are lots of examples of this, which I'll skip over due to time reasons. So these are just, this is a list of important results about how Fourier analysis helps with learning, and something we do in our paper, which we weren't able to find in the literature. Probably in the literature, it exists with a worse prefactor. Okay, finally I can do something quantum. So all of this was classical. Now, how do you talk about quantum learning in this framework? And the idea is you change the example resource. So what I'll be talking about is a framework called learning from superposition examples. Here you imagine that you're given copies of a certain quantum state. And this state has the following form. So it's a superposition state over computational basis vectors. And the amplitudes in the superposition are determined by the probability distribution.
It's quantum pack.
It's the quantum pack model. This is the quantum pack model introduced by Chauty and Jackson. So this encodes the probability distribution in a quantum way. And now your goal would be to learn this unknown distribution, as I just said, so to learn a function that agnostically matches it, by performing a measurement, post-processing it, and then outputting a hypothesis. So what we've changed is the resource, and what we've changed is the fact that you can do quantum computation. But the requirement is going to stay the same. And now, very, very simplifying this a lot, we know something we can do here which is called quantum Fourier sampling, and it's absurdly strong. So if you give me one of these superposition examples, I can use quantum Fourier sampling to, for example, learn parities, learn disjunctive normal forms, or learn Fourier sparse functions. And essentially the way this works is that this kind of quantum resource via quantum Fourier sampling gives you access to the Fourier spectrum, and the Fourier spectrum is super helpful for learning. Now let me point out the subtlety here. This is for the functional case, so where you have a deterministic function describing the mapping from inputs to outputs. There we know how to do this. If you go beyond the functional case, we don't. So, with the small caveat that we can do it maybe if there's a little bit of noise. But in general, we don't know how to do quantum Fourier sampling for these superposition examples if they really come from a distribution. And given that quantum Fourier sampling is behind most of what we do in quantum computational learning theory, this is a big issue, at least for me. So this was the first issue that we addressed in our work. So we saw this problem that we can't do quantum Fourier sampling. And the reason we chose to attack it was to look at a new kind of resource that you could have quantumly. So let me first describe in a cartoon what that resource does. So if the quantum learner asks for a single quantum example of the distribution, then what the oracle does internally is to say, okay, let's pick a random function where the distribution over functions has to do with the distribution. I'll say more about this on the next slide. And then I'll just prepare a functional superposition example, and I'll give that to the quantum learner. Okay, so the example that's sent is a functional quantum example, but the function in there is not always the same. It's a function drawn from a certain distribution. Something like this has recently also been studied in complexity theory. They call it non-standard quantum oracles or mixture oracles. This is something similar. I'll call it mixture of superpositions or just MOS because I'm lazy. Mathematically, you can write this quantum example in this way. So what you do is you take a mixture of pure states, and the mixture is according to a probability distribution over functions. What's that probability distribution? It's the only one you could reasonably choose. So the probability of getting a certain function is you look at each input independently, and the probability that the function outputs 1 is the probability that the distribution gives you the label 1 on that input. So this is what this expression says. You have a product over all inputs are treated independently, and then you look at the probability that the underlying distribution D assigns the value Y. Why is this the only distribution you could choose? Basically, it's the only one that passes some sanity checks. The first sanity check is if you look at the functional case, our example just reproduces the already existing notion. And the reason why you have to choose this distribution is if you measure in the computational basis, you want to end up with classical data. And if you choose this distribution, that's going to be the case. If you choose any other, I suspect it's not going to be the case. Okay, so this is a new quantum resource that we introduce. So why all of that? The reason was this conflict that we didn't know how to Fourier sample in the agnostic setting. And now the nice observation that we have about our new kind of example is it allows you something that's almost as good as Fourier sampling. What it allows you to do is, with the procedure that you know from quantum Fourier sampling, so just apply Hadamard gates everywhere and then measure in the computational basis everywhere, what you get out is, okay, the last bit is 0 and 1 with probability half. If it's 0, that's kind of useless. If it's 1, it's useful. Because if it's 1, then the probability that the first n bits equal some string s is inverse exponentially close to the square of the Fourier coefficient of s. Okay? So these Fourier coefficients are what we want. If we understand those, then we can learn. And what this theorem says is that this new quantum resource allows you to sample from something that essentially is that Fourier spectrum. The Fourier spectrum is not a probability distribution. It's not properly normalized in this case. So there has to be some error, but the error is extremely small. All right. So we can do something like quantum Fourier sampling, even in the distributional agnostic case, with this new kind of quantum data. And then I'm going to skip over a few details here. So why even do quantum Fourier sampling? The underlying important result is if you can sample from that distribution, you can approximate it. Mathematically, this looks as follows. If you don't look at a ridiculously small accuracy, so if your accuracy is not inverse exponentially small, then, and you give me on the order of 1 over epsilon to the 4 copies of the mixture of superposition example, then we can efficiently produce an approximation to the Fourier spectrum. So we can produce a phi tilde that on the one hand is epsilon close to the true Fourier spectrum, and on the other hand it's going to be succinct, by which I mean it has few non-zero entries. So the number of non-zero entries is like 1 over epsilon squared. All of this works with high success probability.
Sorry, but epsilon could still be exponentially small, right?
It could still be, yeah, okay. It could be exponentially small, just not this specific, this specific exponential. Yeah. Okay. So takeaway message, given a number of copies of this state that only scales with the desired accuracy but is independent of the system size, you can get a good approximation to the unknown Fourier spectrum. And then the next step is, oh, sorry. I'm going to make this assumption for all of the next results, but I'm too lazy to write it out. Yeah?
Could I get some intuition for why it's independent of the system size?
Yeah, so why it's independent from the system size is a super cool result called the DKW theorem by Dvoretsky, Kiefer, and Wolfowitz, which tells you about how you can empirically approximate cumulative distribution functions. And there you can get something independent of the size of the support of the probability distribution. Mathematically, that's because the VC dimension of step functions is 1. I'm not sure whether that's of any help to you, but this is the underlying magic behind this result.
But it's because you have the inf norm, right?
Yeah, sorry. That's another thing. It's because you have the infinity norm here. That's also true. If you wanted a 1 norm, then you would, of course, get a dependence, unless you have sparsity assumptions or something. OK. Yeah, Robin.
On the previous slide, if I wanted to just compare this with the case of Boolean functions, like how would this theorem change? Like would the parameters get better? Or?
If you do the case of, if you look at the case of Boolean functions, I guess the big change is you can't do it from examples. You would need something like queries to do a Goldreich-Levin algorithm. So there's no classical procedure that can Fourier sample from examples of the distribution. But if you have query access, you can do stuff like Goldreich-Levin, and it achieves similar dependencies. But it does depend on the number of bits.
I guess what I meant is like your setup, but it's not a mixture of samples anymore. It's just pure samples because we know it's a Boolean function.
But it's still quantum examples. Sorry, yeah. Essentially same dependency.
Okay, so the epsilon is also to the power 4, and this all of that is the same.
At least I think so. Yes. I think the scaling is the same.
So this is like just a strict generalization, or it's like
yes.
an upgrade.
Yeah, it's an upgrade, and it reproduces the functional case. Like this, like this 1/2 to the n thing actually vanishes in the functional case, and then you reproduce the Boolean result.
Isn't it just exact if it's a Boolean function?
Yeah, in the Boolean case, it's exact. And what we're showing is even if you're far from Boolean, it's still approximate. OK. I think I'm going to skip the proof. As I said, if you want to understand how it goes, this DKW theorem is amazing. And with it, you can solve that problem. OK, to kind of conclude my stuff about learning before I get to verification, let me show you in action how this Fourier spectrum approximation can help you. So why would you want to approximate the Fourier spectrum? One example is you can use this for parity learning, even in an agnostic scenario. So what you get as a corollary of this is, if you have a number of copies of this state that essentially scales like 1/epsilon⁴, we can efficiently produce an n-bit string that achieves the agnostic learning guarantee where the model and the benchmark class are parities and alpha is 1. So what I mean by this is, if you draw a new sample, the probability that the inner product of your bit string with the with the input bit string disagrees with the label is at most the optimal probability you could have achieved with any possible bit string plus epsilon. Okay? So in this case, in fact, the model class and the benchmark class are the same. So long story short, using these mixture of superposition examples, you can extremely efficiently learn parities. So this is sample efficient, computationally efficient, memory efficient, essentially whatever you could ask for. It's even independent of system size. And what I want to highlight is, this is super hard classically. Classically, if you were given these like the classical analog of these examples, you stand no chance, because it's at least as hard as learning parities with noise. So in fact, this being n-independent is like unconditionally better than you could get classically. Classically, you need a linear and n dependence here in the number of samples. And computationally, we have no efficient algorithm classically. But this is a computationally efficient algorithm quantumly. Now, we're not the first to do this. There was an efficient quantum LPN and LWE algorithm before us. But that one was only for function plus noise. We can do the general agnostic setting. OK, so this is the parity case. I'm going to skip the Fourier sparse case. It's essentially the same. You just have a Fourier sparsity parameter. But I think I'm running a bit low on time. Let me just say that this is why we had to introduce the alpha. Because in the Fourier sparse case, the analysis becomes annoying, and you get a prefactor 2. I would very much like to know how to remove it. But I dug through a lot of classical learning theory literature. And the best that they can do is a prefactor 8. So in the end, I had to be happy with a prefactor of 2. But OK, so I've talked a lot about learning theory now. But let me try to remind you of what I'm actually going on about. This was the final goal. Find the learning problem that's classically intractable, but quantumly solvable, and that we can verify. What I've done so far is I've shown you how to check box 1. I've shown you that, for example, the problem of agnostic parity learning is a good candidate here, because it's classically hard, but with this quantum resource that we introduce, it becomes feasible. What I haven't talked about so far is step 2, and this is what I'm going to do now. So let me tell you about the verification part. And now, this is another way of looking at it. So our perspective is, I'm a client. I'm paying for a service provided by Google, IBM, whoever. So with this, I outsource computation to a server who has access to a server oracle. And actually, for the purposes of this talk, the server oracle will be quantum examples, but it could be anything else. And similarly, on my side, I could have different kinds of oracles. And the goal is that after this interaction, I output a good hypothesis. This is the picture you should have in mind. Before showing you the results, let me be an annoying mathematician here at IPAM. I want to be transparent about two assumptions. So we have to make two assumptions to make the verification work. These assumptions are not needed for the learning I've showed you so far, only for the verification. The first thing we have to assume is that the unknown distribution has no small non-zero Fourier coefficients. What I mean by this is, if the Fourier coefficient is not zero, it has to be above some threshold. And our results are going to scale inverse polynomially with that threshold. This is the first assumption we have to make. The second assumption is that we have some a priori knowledge about the L2 bias. So what I mean by this is that the expectation of the square of the conditional expectation is in some interval a squared b squared. These seem like technical assumptions, and they are. I just want to say two words about them. So the first is, these assumptions are satisfied in the noisy parity learning case. I'm not going to tell you why, but it's relatively easy to check. And it's also satisfied in the noisy Fourier sparse function case. So in particular, if you look at the classical agnostic learning problem for distributions that satisfy both of these assumptions, it's still classically hard, because it's still more general than learning parities with noise. So by imposing these additional assumptions, I am restricting the class of learning problems, but it still contains classically extremely hard problems. OK, now with the assumptions out of the way, let me actually tell you what we're doing. So remember that a central ingredient in the learning procedures was quantum Fourier sampling and Fourier spectrum approximation. So the goal now is, for a first step, to verify this specific subroutine. So I, as a classical verifier, want to interact with a quantum prover so that in the end, I end up with a good approximation to the Fourier spectrum by using the interaction with the quantum prover. And so I think this is the most challenging slide of my talk. So I'll go through it very slowly. This slide has two purposes. The first purpose is I want to show you the result. The second purpose is I want to define what I mean by interactive verification. So this will happen as I explain the result. I hope this works. If it doesn't work, please ask me questions. So first, let me get the assumptions out of the way. I need the threshold to not be absurdly small. I need the accuracy to be, the desired accuracy to be lower bounded in terms of this assumed L2 bias. And then I need the unknown distribution to satisfy these two assumptions. And now what we show is that there is a pair of a classical verifier and a quantum prover. So these are algorithms that satisfy the following. First of all, the prover is efficient in the sense that the number of copies of rho that it uses and the computation time that it uses. And when I write computation time here, I mean quantum computation time, so the number of gates that it applies. These scale nicely with, in this case, the threshold and the system size. So we have an efficient quantum prover. We also have an efficient classical verifier. So this classical verifier uses classical examples and classical computation, both of which are efficient.
So sorry, I mean, but one allows it to be exponential in n, right? Because you only demand your theta to be, it can still be exponentially small.
Yeah, that's true. But if you ask for like exponential accuracies, you expect to be exponential in n, and it's similar with this threshold value. I mean, if epsilon is like exponentially small, then the same happens in classical learning theory. Yeah, I guess you should think theta. I think of theta as maybe a constant or like 1 over a small polynomial. OK, so both the verifier and the prover are efficient algorithms. And now comes the, oh yeah, Robin. Yeah, they're hidden in my assumption. So I have to assume that the square is like in some interval. If this were the Fourier, the function case, a and b would both be 1. If it were a noisy function case, b would be 1 and a would be a little bit less than 1. You can go beyond this. I'll comment a bit more about the assumption later on. I hope that clarifies it then. OK, and now comes the part where I A, show you the result, and B, give you the definition of what I want. So the first aspect is a completeness guarantee. So what I want is, if this verifier V interacts with this specific quantum prover P, so the honest quantum prover, then after the interaction, V outputs a good approximation to the Fourier spectrum. Here I've changed to the 1 norm, which doesn't hurt so much because of this thresholding assumption, so it's sparse. You could also write it with an infinity norm, then you would get rid of the thetas. So if the prover is honest, then after the interaction, the verifier has solved their task. They have achieved the Fourier spectrum approximation. That's what a computer scientist would call the completeness requirement in an interactive proof. But I also want a soundness requirement. So soundness means if the verifier interacts with some prover that does something wrong, that could happen because the prover is lying. It could happen because the prover is not powerful enough to do what they're supposed to do. It could happen because the prover is just incompetent and messed up. That doesn't matter. So no matter what possibly infinitely powerful prover the verifier interacts with, the probability that the verifier still says, oh yeah, this is fine, and then actually outputs something bad is very, very small. So it could happen even for a magical reason that the verifier still outputs a good approximation. This is never going to happen, but in principle that could happen. Basically, you should imagine if the verifier interacts with a dishonest prover, the verifier is going to notice that the prover is trying to cheat, and the verifier is going to reject the interaction and basically say, I paid for this service, but you're not doing it properly, give me back my money. Okay? So this is the definition of interactive verification here, completeness and soundness, and then you have to formulate the requirements you aim for. In this case, it was a Fourier spectrum approximation. Okay. Questions about the theorem statement? Okay. Then let me show you a high-level sketch of how we prove it. We have like 3 different proofs for like slight variations of this theorem. I'm showing you the one that I think is easiest to explain. So here's how our protocol works. The first thing is V just asks P to send a list of all relevant Fourier coefficients of the unknown distribution. And then, okay, P is a quantum prover with this quantum example access, so they can use the Fourier approximation procedure I showed you before to solve this problem, send such a list to V. This list is actually going to be reasonably short because of this threshold assumption. Now, if the prover is honest, V can just stop, right? V now has the correct list and can work with that. But the prover might be cheating, so V has to use some kind of clever double checking. And in this case, it doesn't even have to be so clever. Basically, what V is going to do is to say, OK, I have classical examples. With these, I can estimate Fourier coefficients. So what I'm going to try is just estimate, for all the coefficients that P sent me, I'm going to estimate their values. And then I'm going to check whether the total accumulated Fourier weight of these estimates is large enough. If it is, I'm happy, and I just take this approximation. If there is not enough total accumulated Fourier weight, then the verifier is going to say, oh, the prover might be leaving out an important Fourier coefficient here, so I better not trust them. So in this case, they abort the interaction. This is a very high-level idea. The technical analysis is a bit more intricate. If you're interested in that, please take a look at the paper, but I hope this makes the high-level idea clear. So the important thing is that the verifier can use their own oracle access to check whether the thing that they got from the prover is a reasonable estimate. And they do that by checking the accumulated Fourier weight.
Just understand, so the verifier cannot produce all of the Fourier coefficients, because if they could, they would be it. No. They can randomly choose a subset. That's the point?
Yeah, so the point is that essentially there's 2 things happening. So P does kind of a pre-selection step. So P tells the verifier, these are the relevant Fourier coefficients you should look at. And those aren't that many. And for those, the verifier just estimates all of them, because there's like, think polynomially many. So the important part is that the prover can do like this selection of relevant Fourier coefficients. And that's kind of what this 3rd step is checking. So the 4th step is checking whether the selection was reasonable.
No, it gives the advice.
In a sense, yeah. Okay. And notice that this is actually not particularly interactive. It's just 1 round. One variant of the protocol would be interactive, but this one isn't. Okay. This was Fourier spectrum approximation, but I've been going on about learning. So let me just show you the learning variant of this result as well. And I hope this can reinforce the notion of what I mean by verification. So it's essentially the same kind of box. It's the same assumptions that we had before. We again have an efficient prover, and we have an efficient verifier. And then now the completeness and soundness requirements are going to be for learning. So if the verifier interacts with the honest prover, then for parity learning, the verifier outputs a bit string that achieves a misclassification probability that's at most epsilon more than the best possible misclassification probability. So this is exactly the learning requirement that we had before. If the prover is dishonest or incompetent or whatever, then we just want that with very low probability does it happen that V accepts and outputs a bad bit string. So a bit string that violates the agnostic learning criterion. So this is the whole trick about this definition. You want, if the verifier interacts with the honest prover, it solves the task. If it interacts with a dishonest prover, then the verifier should, with high probability, reject morally. So I want to emphasize something here. So as I said before, this class of learning problems includes learning parities with noise. So the verifier on their own is not able to do this. But by interacting with the prover, the verifier can do it efficiently. And nicely, the prover is also efficient. Let me emphasize this asymmetry as well. I want the honest prover to be efficient. The dishonest prover can do whatever they want. They might be computationally unbounded. OK. Yeah?
Within this scheme, I mean, it's never conceivable to have like multi-rounds of interaction, right? Because like in entangled theory, we have these settings that we have, for every k, you can reach more states in k-round interactive settings compared to like k-1.
Yeah.
But that's not.
Yeah, so that's a good question. So the framework in principle allows for it. Our result doesn't use it. And as our result is, as I'm going to say soon, almost optimal, you don't need it here. But there are examples of these interactive verification tasks in the classical literature where they use really multiple rounds of interaction. I'm, however, not aware of proofs separating them according to how much interaction is used.
Okay. I had a question on the role of theta here. How does it show up in the claim, in your claim?
So it shows.
3 and 4.
It doesn't show up in the claims 3 and 4 at all. It only shows up in the amount of data that is used to guarantee these claims. I can give you a high-level idea. The high-level idea is you check the accumulated Fourier weight, which is bounded by like b squared and a squared. And you know that every non-zero Fourier coefficient accumulates at least theta squared. So how much can there be? Well, it's like b squared divided by theta squared. And that's why this, OK, there's going to be an additional square, but that's the technicality. That's why this appears in the sample complexity. So it appears in the resource requirements. Robin.
The comment you made about learning parity with noise, it sounds like then you get a polynomial time quantum algorithm for solving learning parity with noise.
Very good point. I'm not claiming that quantum computers can solve learning parities with noise from classical data. I'm claiming that quantum learners using quantum data can solve the problem. So this does not break any of the standard crypto protocols because they're based on feeding classical LPN data into a quantum computer. I'm changing the oracle.
It's specifically the MOS data, right?
What do you mean by MLS?
The MOS.
Oh, the MOS. Sorry, yeah.
You need that data.
I need that specific MOS data. OK.
But you can solve learning parity with noise with even weaker data. Like this weaker quantum oracles that you could also use.
Yeah, that's true. So for learning parities with noise, basically you have to think about how do you do functional plus noise. I'm aware of like 3 models. One of them is generalized by ours, and there's 2 others. And for all 3 of them, you can do it if you have the right notion of quantum data. All right. Now, let me just, OK, I'm going to skip the Fourier sparse part again. I want to say one more thing. We have these weird lower bounds on the accuracy in terms of this difference of the bounds on the L2 norm. They bothered me for a long time. I just want to say that we looked into it, and this is essentially optimal in the following sense. If you want to get a verification theorem like the one I showed you, and you want to achieve an accuracy that's even a little bit better, it's like 1/3 times this, then what you lose is the n independence in the sample complexity of the verifier. So as soon as you require this, the verifier will have a sample complexity that depends on the number of bits. whereas in our results, it was independent. So in that sense, it's optimal. You can't improve this requirement more, significantly without paying a potentially large price in the sample complexity. And for this, I've given you like several proof sketches. I want to do one last one. And this is an idea taken from a paper by Matthias and Schaffer, which I find beautiful. So on a high level, how do we prove this? So this almost optimality. What we do is we say, if we had a classical quantum pair verifier improver, we can use this to build a classical distinguisher between random noisy parities and the fully uniform distribution. And that's known to require omega of n samples. So if the verifier used less than linearly in n many samples, that would violate a bound. The one thing that you might be worried about is here, this is a classical lower bound. So why can we use that? And this is the part of the proof that the proof idea by Matthias and Schaffer that I find amazing. So I want to give you the cartoon. So how does this reduction work? And keep in mind, we want a classical tester. So uses only classical data and classical computation. What happens is it takes in classical samples, and then it's going to emulate the verifier prover protocol in a clever way. So it's going to feed those samples to the verifier, and it's going to simulate a prover, but a prover with access to a completely useless quantum example. So with access to the oracle for the complete uniform distribution. No information whatsoever. Uniform both over inputs and outputs. So in particular, this is a known state and a known oracle, which you can simulate. There's one caveat. You're still simulating a quantum computation, so it might be costly in terms of the classical computation time. That's why our statement is only about sample complexities, where you don't pay this price. I suspect that because you're simulating something on a maximally mixed state, it should even be computationally efficient classically, but we haven't tried that. So what the distinguisher now does is simulate this interaction between the verifier prover protocol and then add one single step. And that single step is to check whether the hypothesis that the verifier produces performs well. And that they can check by feeding in some more samples. And now they just distinguish two cases. The first case is if the hypothesis is either a reject, so the verifier rejected the interaction, or H performs well, then they're going to say, OK, that was a noisy parity. If anything else happens, then they're going to say fully uniform. And why does that work? So roughly, you see here, we have, imagine it was a noisy parity. Then this is noisy parity data, but the prover has fully uniform data. So the prover is just dishonest because they have the wrong oracle. They can't do much better. So we have a verifier interacting with a dishonest prover. So basically, by our soundness guarantee, it's going to reject with high probability, which means we essentially end up in this case. If it doesn't reject for some magical reason, it's still going to perform. It's still going to perform well because it's a noisy parity, and we can reasonably well approximate noisy parities. If this is a uniform distribution, then we're interacting with an honest prover. So by completeness, this verifier is going to learn a good hypothesis, but it's good relative to the uniform distribution, and you cannot be good with respect to the uniform distribution, so you're going to perform badly. So this is how this reduction works. And as I said, this is not our idea. It's from the Matthias-Schaffer paper. Our contribution is to say you can even do this with quantum prover over here, because the simulation is for like this fixed quantum state. OK. I'm unfortunately going to have to skip the limitations. Let me just say the quantum data oracle we introduce is not arbitrarily powerful. There's things it cannot do, and it's roughly the same things that the superposition examples cannot do. So from that perspective, it's not an absurd resource. But as I said, I'm unfortunately going to have to skip this, even though that proof is also nice. And let me conclude. So this was our question. Can we find a learning problem that's classically intractable, quantumly feasible, and that a classical verifier can outsource efficiently to a quantum prover? And what I hope to have done is to convince you that like these mixture of superposition examples are, for the agnostic scenario, a powerful quantum resource. In fact, in the paper, we do a lot more than what I just told you. We do quantum statistical query versions of this, and we investigate which parts of this you should be able to solve. But I thought that might be a bit much. So if you're interested in that, please look at the paper. And then we use that resource to identify problems that are classically believed to be very hard, but that become efficiently solvable when a classical verifier interacts with a quantum prover. Now, maybe the most important part of this talk are my open questions. So I am not claiming that anything of what I've showed you is practically relevant because of the quantum data that we used. I don't know where to get that from. What I'm hoping is to inspire some questions. So for example, the first question is, we introduced this new kind of resource because there was something we couldn't do with the old kind. Now, I can't do it. That doesn't mean it's impossible. It just means I don't know how to do it. So to the best of my knowledge, there's no proven separation between the PAC examples from Chowdy and Jackson and our new one. So I think it would be interesting to see whether they can be separated. We have indications that in the distribution-independent case, they cannot, but I don't know about the distribution-dependent case.
Yes, but you could generalize your thing by looking at the purifications of a mixed state, right? We
Yes.
have an indicator, but then we might be even more powerful.
You could. I have no idea what helps, whether that helps. You have to be careful about one thing. If you purify, you don't want the unknown function to be in like the purifying register if the learner has access to that. That would be too much information.
That's what I'm saying, that you could do a lot more.
Yeah, like then you can trivially solve problems. Like we give some examples where I have some examples of variants of the oracle that become trivial. Okay. Now, the second open question is, this was a specific scenario, namely in quantum computational learning theory. I think this verification question, where there's a mismatch of power between two parties, is important more generally. So for example, I think it would be interesting for other learning scenarios, say distribution learning, where as Jens pointed out, we already know some separations. Or what we're currently working on is to take this into the framework of learners with a lot of strong quantum resources, large quantum memory, quantum coherent processing capabilities. And that would be the prover, but maybe the verifier is super weak and can only do like single copy measurements or something like this. And here, so far, we have some no-go theorems. So in some cases, it doesn't help a weak quantum prover to interact with, a weak quantum verifier to interact with strong quantum provers. Fortunately, we're also starting to find some first positive results, so maybe it's not all bad news. And the final direction that I think is interesting would be NISQ-friendly variants of our framework. So you could think about either the verifier being NISQ, or the prover being NISQ, or both being NISQ. So all of these variations, I think, would be interesting. And then you could also ask these questions in the context of variational quantum machine learning, which I haven't touched on in this talk. All right. That's it. Thanks a lot for your attention. And now if you have any more questions, please go ahead.